Hi, I'm Chuck Abrahamson. I am with ABR Industries, and today I'm going to talk to you about different types of coax and connectors. A little bit of information about myself. I'm a partner at ABR Industries. My focus is on the sales, marketing, and technical side of the business. I'm in the wire cable business since 1991, and I've been involved with amateur radio since 1998. My call sign today is actually K9CFA. So we're going to focus on three different areas. First is an overview on coaxial cable, a little bit of history, some key terminology, material overviews, and then we'll get into some deeper dives as far as cable that are popular with the amateur radio community, more regarding the design and performance, where they use as far as the applications go as well. And then we're going to wrap up a little bit of the back half with connectors, more or less the popular types that are used today, as well as some background on those different connectors. So what is coax cable? Well, coaxial cable is a interconductor that has a dielectric and then an outer metallic shield and then a plasticized jacket. It's typically used in applications starting from 1 megahertz and above. There is a maximum range for coax cable, which typically tops out around 12 gigahertz. It's used for broadband, trunking lines, high-speed computer buses, cable TV, a wide variety of different radio transmitters and receivers. We see coax in the amateur community quite often. Coax cable was actually first theorized in 1858 by an English physicist. Oliver Hebside, who patented the design, didn't realize what he had come across. He was looking for a way to move DC current from one place to the other, but didn't realize that his concept was actually going to be more useful on the AC side of things as that was coming about. Oliver's product really didn't come into the play until 100 years later when the coax became a mainstay in our community and used globally. So the first thing we're going to look at is the impedance of the coax. A coax is typically three different impedances: 50 ohms, 75 ohms, and 93 ohms. Audio is at 50, video is at 75, and 93 is at networking. And this came up with the US government back in the 1930s. Characteristic impedance is what we look at as a uniform transmission line where the amplitude and voltage of a current wave propagating along the coaxial line is in one direction, absence of any reflections in any other direction. So that means we're looking at this with a 1-to-1 SWR ratio. So how do we calculate the impedance of a coax? Well, we look at the square root of the inductance and capacitance. We look at the dielectric constant, and then we look at the log of the two different diameters of the center conductor and the outer braid. So let's take an example. When you look at RG213, we know the dielectric constant is 2.3. The outer diameter comes to 0.32 inches. The inner diameter is at 0.092 inches, which when we do the math means that we get a 49.2 ohm coax. Now coax's typical tolerances are plus or minus 2 ohms. So it's pretty easy, right? It's pretty neat. And when it comes to a good manufacturer, the challenge is to make sure to use a very good 7-strand center conductor that comes out to 13 gauge, as well as a 97% braid to meet the correct outer thickness. Next, we'll talk about the velocity of propagation. Velocity of propagation helps us understand the loss characteristics of a coaxial cable. Every insulator except air does reduce that velocity. Also, every insulator except air reduces the wavelength. So both effects are dramatic when you look at the dielectric constant. So for the first picture, you can see we've tested all of these cables 1 gigahertz. For air, it would take 1 nanosecond for it to travel 1 full wave. We look at the foam dielectric, it's at 1.5. And that means that it changes that spacing down to 24.5 centimeters. Teflon PTFE typically runs a little bit less at 21, and when you look at solid poly, it's at 20. So to do the math a little bit backwards, the air is at 100%, the foam PE in this example is at 77%, the Teflon PE is at 70%, and the solid poly at the bottom is running at 66% velocity of propagation. So when we look at the velocity factor of our RG213 example, we see the velocity factor is 100 over the constant that we talked about earlier, which is that 2.3. So for RG213, the velocity is 100 over the square root of 2.3, which comes out to 65.96, which is 66%. So as we look at that, we also measure then what that time delay is, do that characteristic calculation, and get 2.34 nanoseconds. Now, remember the math is never perfect, so when we look at that, we look at an average range of plus or minus 5%. And then the final thing is the maximum usable range of the coax itself. That goes back to the diameter of the coax and the cutoff frequency that we need to check for with the dielectric that's being used. So for example, 213 actually works very well up to 12 gigahertz. So why do we list some cables up to 6 or 8 gigahertz? Well, a lot of it came in from the testing side. So here's a hint. The BNCs that we used actually were limited up to 6 gig, which was the original standard that we followed when we started tracing this back in the 1960s for the cutoff frequency. Now the next big piece is attenuation. Attenuation is the big gorilla that we look at. We always look at losses. We always try to worry about maximizing our signal output. So for us in the US, we do this in dB per 100 feet. The rest of the world uses meters. Sometimes they use meters as 100 meters. Sometimes it's 30 meters, which is closer to what we use. So an attenuation in dB comes out with a couple different factors. One is we have to understand the frequency. Two is we look at what the skin loss is, which is the outer loss of the product. Then we look at the dielectric loss, and from there we can make our calculation. So with 213, the K1 value, which is the skin loss, is 0.17. The dielectric loss is 0.002, and we're going to use 30 megahertz as our frequency. So for our calculation, we come out at 0.99 dB per 100. In a lot of cases, we will round up, and in this case, it's 1.0 dB because we try to take into account the connectors that are being used. Now, we're not trying to make things look a lot worse so that we can cover ourselves, but trying to make it as practical as possible for people to understand when they get the products out there in the real world applications. So here's a list of popular insertion losses of different coaxes, picking stuff from the ABR 600, which is a little over half an inch, the two popular RG8 replacements, the 400, which is a solid, and the 400 Ultraflex. There's good old 213 in the middle, and then a couple of other things, the 240 products in a solid and an Ultraflex. Now, a lot of hams love the 240 Ultraflex for portable applications, vehicles, using it field days, jumpers in the shack. We look at old RG8X, as you can see there, it's quite lossy in comparison to the new products that we're using today, and I'll talk about that when I go through the data sheets. And then a few other things. The 195 product replaces 58, very much popular in automotive applications. And then RG316, which we call affectionately ABR 316, which is the little Teflon guy. Seemingly very lossy because these calculations are done at 100 feet, but when you look at 2 to 3 feet, even 6 feet, it's very reasonable and it's very manageable for a lot of hams to use. So how do we worry about return loss in SWR? Well, as we know that from our calculation, return loss is 10 times the log of the forward versus the reflective power, or 20 of the log of the R value that we just came up with. So when we look at VSWR, we look at this as substituents and reactants. In this case, we look at VSWR as the scale that you see there in the middle, and then the return loss as in how much power is completely coming back. So what happens is when we have a lot of power, all of it coming back, it's close to infinite, well, we're not very well matched. But as you notice, we get closer to about 2 to 1 SWR, then we start to see our matches get better, not great, but better, and then our matches really become very well matched at 1.2 to 1 and downwards. Just as a piece of information for everybody, connectors are calculated at a couple different frequencies now. They start off at the DC value, which is what most people see in the charts, but there is a separate calculation that's done at usually 2 gigahertz, 4 gigahertz, and 12 gigahertz. So the next we're going to look at is the center conductor of the coax itself. As you can see, copper is the most popular. It's out there, plentiful, it's easy to produce, it's easy to mill, and it's very, very easy to recycle as well. Tin copper can be used, and in some cases we do that with stranded centers to make it easier to solder to. So that adds about 10 to 20% though of the cost of the overall product. And then even if we silver plate the product, it can double, and if we go with pure silver, it will actually triple the cost of the product itself. Solid center conductors are an average of about 10% lower loss. There are some trade-offs. One is the bend radius due to the memory of the coax and the pressure on the dielectric. And also, if we use a copper-coated aluminum, which has become more popular because we can use it for the skin effect value, we have to actually look at limiting the amount of flexing because copper will crack and then it'll change the skin effect of the product itself. Stranding is very popular because it adds a much longer life and a much sharper bend radius. It can even get down to about 1.5 inches in most cases. And the other thing with stranding is it's easier to bend, move, and flex as you use the coax. Next is the dielectric. There are 4 different types of dielectrics that are most popular for amateur use. There are others, but for amateur use, the first generation that we really gravitated towards was the solid poly dielectric. A solid poly dielectric, though, had a limited velocity of 66%. But the important thing was the impedance kept very, very stable as it bends and twists, and it also handled the heating and cooling much better than foam types. So when you think about this for HF applications, if you're running the legal limit, there's a lot of heat that will be generated. You may want to look at RG213 just because it'll last longer than sometimes the gas injected foam dielectrics. The next is the Teflon products, PTFE, higher power and lower loss, a little bit different velocity range, as you can see, 78 to 85%. But the important thing about Teflon is it's phase stable, especially at high temperatures. So it's great for repeater applications, for matching networks, for satellite. And when you put that in conjunction with the silver product there, you actually get a real nice winner of a product. So like RG142 or RG400, or even the big brother RG393 has been very popular. The one change was we started looking at those different products and they became very expensive. So that's where the foam polydielectrics are used. Originally back in the 60s, foam polydielectric of a 75% velocity was released. The nice thing was it was 1/3 of the cost of using any FEP Teflon products, and the bend radius was very, very, very much improved at 1.5 inches. From there, we got even better where we started to introduce nitrogen into the line. There we could get the ultra high velocities that you see today with the 80% plus, which is extremely low loss. And the nice thing is it can handle power very similar to a solid poly dielectric as well. The next is the shielding. When we look at the different pieces of the shielding, first is the woven braid. Copper, tinning the copper, and silver are the most popular. Braid coverages in the market can be a little bit misleading because some braid coverages can be as low as 65%. That can be pretty leaky. Typically, for most amateur use, using a product that's 90 to 95 plus is going to be much more desirable because you don't want to cause any interference with the equipment inside your shack or with anybody else's equipment around you. A couple of other benefits, you can put a foil in there. It's usually an aluminized tape. The foil is typically bonded to the dielectric to prevent any tearing or gaps. The one thing is it will also be limits because with a 95% braid, the foil can actually be cut as the braid is put over it. So that's why you can only see about a 95% braid coverage on those products. And then the final type of shielding is a corrugated copper. It offers the highest coverage, but it's extremely high priced. It also oxidizes and can have moisture migration issues over a 10-year period, which would lose a lot of its conductivity. So even though that helix that you might find might seem like a great deal and might have been very low loss and very efficient at the time it was created, if the copper is turning very, very dark brown or gray or even green, which is worse, then I would suggest maybe looking onto something else. And then comes the shielding itself. So when we look at how it is, usually a foil and a braid is one of the most common that we see in the amateur market today. It offers a very high cost effective design, and the nice thing about it is using tin copper with the aluminum, you get the best of both worlds because it's got a limited reaction and low oxidation. You can also look at some double shielded products like RG214, for example, where RG214 has two woven braids in there, which then limits any of the issues with the bending and twisting or any issues of the foil potentially breaking over high flexing applications. A lot of cases, this 214 product you would see though would be great for repeaters, but may not be practical for a line that's run out there to a standard vertical antenna outside. And then there are some triple foil and braid combinations out there. They're typically used in computer applications or some applications that are 18 gig and above. They can be very difficult to bend and they're usually very, very expensive, but every so often somebody may run across it. And the jacketing itself. This is probably the most critical piece because when we look at coax, one thing to remember is coax is like a set of tires. The more you use it, the harder it's run on, the more difficult the environment it's in, the sooner it can wear out and that it'll be needed to be replaced. But there's a couple things that you can do to help yourself. The jacketing is one of the key factors that a lot of hams may overlook and not realize that spending the extra money for a better jacket will save them in the long run. So there are generally three types of jackets that are classified that a lot of people use. One is a type 1. It's a standard PVC jacket, but here's the caveat. Sometimes it comes with or without the UV inhibitor. So the sun is brutal onto most coaxes,
WA2. Yeah, I'm going to abuse.
will start to crack and flake. The difficult thing is with a type 1 jacket, it's black, gray, or white, and it's going to be very difficult to distinguish unless somebody shows you what that looks like. Now, the common rule is to always print on your product the type of jacketing that is used, whether it's type 1, type 2, non-contaminating, contaminating. It should be listed on the product to help people along. The next is type 2. It's a non-contaminating jacket. It's a very popular jacket at ABR. We use it on a lot of our different products that we offer in the marketplace. The nice thing is it comes with an extra compound that supports a chemical resistance when buried and prevents the salt from leaching into the product. So not only is it UV resistant, but it also holds up against the groundwater contaminating the product itself. And then there are type 3 jackets. These are generally listed as chemical resistant products. They could be PTFE or a special PVC product. The ABR 400 is a type 3 jacket. It is a very stiff, robust product, but the nice thing about it is oil and gas resistant. So as it's used here in the markets in Houston and other places, it's very popular because of that feature that it offers. So when we look at coaxial cable types, it's a lot of stuff. It's alphabet soup, but it's all derived from an RG radio grade number, with the process started in the early 1900s for government use. The RG number is a baseline today, though. It should be used as a reference for size, center, diameter. So when we look at different products, we always look at an RG number as a basis of design. So the 400 products that you see out there today are based off of RG8. They're all based off of RG8. Nobody changes the physics on these things. And the reason being is because of the extruders, the different products that are used for the center conductor, the types of braiders that are used, all of its variations on the same theme. So One of the things to take a look at is always making sure which RG number is used. Now, some Europeans use a different sets of standards. Their standards sometimes can make claims, but the diameter may be bigger or smaller or something else may be different in there so that their numbers don't always match up. So I'm going to give you one little hint. When you look at the products that are out there today, you want to look at testing at a couple key frequencies. 30 megahertz, 50 megahertz, 150, 220, 450, and then up to 1.2 gig. Those are standard tested frequencies that are used in the market. It's a baseline that all manufacturers follow. We go much higher than the frequencies I just listed, but it's very important to realize because when somebody says that it's a little bit better at 144 megahertz, well, technically, yes, all coax gets better at 144 versus 150. And depending on how some people round numbers, you got to be careful. So what I'm trying to say is always be conscious of what you're looking at. Make sure to take it home and test it. There's a lot of great test gear out there in the marketplace that's very accessible for a lot of the hams. And if not, find a buddy. There's a lot of hams out there that are very good at doing this stuff, and they've been doing it for a long time, and they won't treat you wrong when they help you test your coax as well. So let's look at the good and the bad between the solid and stranded cables. We'll start with the solid center conductor. One, they're great for fixed mount antennas and equipment. They're lower loss, typically about 10 to 15% better than the stranded counterparts. They're less expensive option. One is because we can use a copper coated aluminum. And they have excellent shield effectiveness. One of the weaknesses of the product though is after a number of bending moments, usually 50 to 100 times, the center conductor can become weaker. It can break a little bit as far as the copper off of the aluminum center, or sometimes the shielding can come up. Stranded center conductor cables. Excellent for applications with constant movement. Rotor, wind, high flexing areas. The high flexibility has little to no signal degradation, so you don't have to worry about that when you flex it in comparison to aluminum. Small turns, easy bend radius, excellent shield effectiveness still, and one of the other things to look at is also that even though it can be 10 to 15% higher, we usually with a well-matched system, a lot of those losses could be mitigated. So next we're going to spend some time talking about the popular cables that are used within amateur radio. We're going to start with the bigger cables and then work our way down to the itty bitty teeny stuff. The first is the 600 size. It's a great 50 ohm cable, very large center conductor at a 7 gauge, high velocity, and huge as far as performance when it comes with a large double shielding. A couple of other things is it's UV resistant. The reason why it's not suitable for direct burial is because typically in most applications it's run along the ground or in commercial applications where it's not needed to be buried. It is designed for high-powered stationary antennas. It works great on HF, but realistically it starts to shine at VHF and above. The next popular cable is the 400 series, which is the most common type that's used in amateur market today. It's a replacement for an RG8 that we discussed earlier on. A good 50 ohm coax with a large 10.5 gauge center conductor. Now be aware that center conductor is larger than you'll see on an average 213 or an average RG8 size cable. We actually do some things where we thin out against the jacketing to still keep the same OD. But with that larger center conductor means you have to buy a PL259 or an N-type connector that is slightly sized larger for this type of cable. It's still very common, become much more common actually since the 1990s, but still it's one thing to take a look at. The nice thing about this product is it's great for stationary antennas. If you're putting up any type of antenna out there that's sitting there without any movement into the wind. Now I would caution people, dipole antennas, yes, are stationary antennas, but do have a tendency of shifting in the wind as things move. So this is good for vertical applications if you're going to use it on HF. But reasonably speaking, as a great product for a lot of entry-level hams on VHF and above, you can't go wrong because the cable is so versatile and nice low loss and handles a great amount of power up to the legal limit. If the installation is a little bit of a challenge, or you're putting it to something that's hooked up on a rotor or going to be flexed, then the 400 UltraFlex product may be the right item for you. It's also, once again, a high shielded product, very low loss, still a little bit higher technically than the solid center conductor, but very, very respectable at L3.3 dB at 450 megahertz. Now that may seem like a lot, but when you look at the application, you can also make up some of your losses with a lot of the high gain antennas that are out there for 2 meters and above. So once again, it's practical for a lot of those applications. But some people still like to use it on HF because it's a lower loss product, and with a lot of the rigs today, they're built as all-in-ones. So if you're going to run one feed line, this might be the best choice for you. Next is the 213. People look at this and say, why do I want the 213 product? Well, that's because RG213 is an HF workhorse. It's designed specifically to be used in a lot of the HF applications 30 megahertz and below. Reason being is because of the heating and cooling effect that happens when you transmit and receive, especially nowadays with more digital modes and applications out there and people using CW on high power. Well, what happens is a gas injected foam type or a chemical foam type will have a dielectric separation based on the heating and cooling effect along the center conductor. Now, because these are stranded center conductors in most cases, that center won't change, so the impedance won't move because the center will relax and bend outwards a little bit to match up with any changes in the dielectric. But if you want to be 100% sure and make it completely bulletproof, 213 might be the product to go with. Also, when you look at the loss characteristics, it's typically a tenth to a 2/10 of a dB at 30 megahertz, and as it goes down in frequency closer to 10 megahertz, it gets even closer. So take a look at RG213 when you're looking at your application. It's very robust, it's great for rotor applications, and good product for field day in some places as well. Now we'll get into some of the smaller types of coax cables. We'll start with the 240, which is an RG8X replacement. There are two versions. One is a solid center conductor and then a stranded. We'll start with the solid center first. So with a solid center, it's a nice low loss cable, UV resistant. It is suitable for direct burial, but typically a lot of people use this in short stationary setups, like apartments, for example. It's great for systems that are 50 feet or shorter, but it's a nice way to hide a piece of coax along a system that could be used in an HOA where people can easily identify it as the same thing as your cable TV line. So definitely something to take into consideration when looking at this type of product. The other version of the 240 is the UltraFlex version, a nice, small, low-loss coax. The important thing to look at 240 UltraFlex is that when you get into the shack, sometimes it's very hard to run big cables. And if you're not running legal limit, but even a 600 watt amplifier, you may want to take this as the choice inside. Running from the radio to the meters to the other devices can be very tight and difficult to bend cable around, especially larger size coaxes. Although losses are always taken in consideration, when you're running even up to about 15 feet, the losses are relatively low or very similar to running a 400 series coax. So for a lot of you, it might be a coax to consider just because it's a lot easier to bend and twist. It'll save you a little bit of money, of course, but it'll also make your shack much more enjoyable without having the equipment picked up because they're so lightweight with a heavier coax. And then finally is the 316. 316 is typically used in jumpers, can be used also for small QRP radios, used out there when they're hiking. It's good for runs of about 10 feet or shorter. Some people use it up to 25 feet, but still, it's usually done with HF applications. The reason this product is so good is that Using the PTFE, it helps reduce any crushes or incidents where the product can get smashed, hit by a rock, in a car door, in a car jam, somebody could yank it, something else could happen. So it's nice coax that's very effective for those types of things. Definitely a product that you would use in a very specific area. I wouldn't quite recommend it for use in vehicles. That's where the 240 usually comes in, or the 195. But I would definitely take a look at this product when you needed to go through a window door jam for an HF application, maybe in an apartment or a house that you're renting. So now let's look at the types of connectors that hams most typically use. So here's a high-level summary of connectors. PL259s are by far the most popular. N-types are gaining ground in their use, but still not very commonly seen below 450 MHz. B and C connectors were starting to fall off with the SMAs for the HTs. However, we're starting to see a resurgence for the QRP crowd. Connectors are rated based on breakdown voltage and maximum current. Adapters are not evil. They won't ruin your system. They are more of a necessary evil. So most people won't see any effect in their system until they get the 500 MHz. A suggestion is always use rotary tools when stripping and putting on connectors. Snips, X-Acto knives, they're great for cutting on straight lines, but they're not very good for cutting on curves. And then multimeters are great for conductivity only, but when testing the dielectric breakdown, that's the most important piece. Beyond that, my suggestion is to look towards some of the TDR products that are out there in the market today. So PL259s, originally invented around World War I, was a great way to connect then the transmitters from something different than open wire, because open wire like ladder line can have a lot of impedance changes based on a slight twist, a bend, the weather. So that's where they needed something much more stable, and that's where the PL259 on coax really started to take hold. It's been redesigned several times. One is to reduce the threads on the back because of overstripping. Next was looking at a larger pin to fit the 400 size. Then we started looking at crimping because we wanted a stronger, better connection to the braid. As with soldering, the braid is only connected at about 120 out of 360 degrees versus the crimp that gets all 360. And then finally, the last thing we've done over the last few years is taper the center conductor. Now, some misconception is that center conductor is smaller and fall out. The diameter of the center is the same, and the power starts from the back of the connector going forward to the tip. So the diameter is the same. The only thing that changed was it slimmed down by 2 millimeters, which is very difficult for people to see. Finally, frequency is now limited up to 500 megahertz versus 300, which is definitely still a positive, but limited. Here's the difficult thing for a lot of people to understand. PL259s are a non-constant impedance connector. It's because of the shell and the shifting and the movement of the connector itself. As you see, there is the way to hook up the ground to the outer body, but the outer body is not stabilized, so as it moves and twists, it creates capacitance or changes the different values based on heat and other limiting factors. And then finally, it's very, very difficult to weatherproof. It has to be completely sealed and wrapped for it to really prevent moisture. So let's talk about, everybody says soldering is better than crimping. A little bit of a misconception there. Older PL259s had 4 weep holes, and as I discussed earlier, in a perfect world, somebody can only solder at 120 degrees as it starts to flood within the weep hole. Gaps then can sometimes form solder joints, which then becomes problematic because those cold joints start to lose conductivity. And then another big problem is the connector is very, very weak, and the pull strength was only at 100 to 200 pounds, which realistically isn't very much. A small child, a 5-year-old, can technically pull something close to 100 pounds. Soldering the center pin and crimping is typically the best method. There's a lot of tools out there that hams can get themselves hands on to. And the nice thing is, with a good soldered center conductor, it eliminates the cold solder joints. The crimping offers 360 degrees of a connection, and the pull strength can be as high as 800 pounds when we use it in a pneumatic press environment, but even hand crimping literally doubles or almost triples the crimping at 200 to 300 pounds. Next is the N-type connectors, typically built for the government for satellite communication and transmitters above 300 megahertz, because for a long time we thought 300 megahertz was the end of the RF world. Extremely durable design, a very constant impedance, designed with a larger pin so it can handle the bigger size coax cables like the 400, which is a larger center than an RG213, for example. A very minimum capacitance bump when installed, and very good intermodulation. A lot of N connectors are rated up to 18 gigahertz. They're very stable, like I said, because of the inner ring, so the impedance never switches and moves. And then they're very easy to weatherproof because they have a gasket that's built into them. Now onto the BNCs. Originally designed for small handheld devices, mostly test equipment at the time, a very robust design because when you're testing, you're taking something on, taking it off, taking it on, going on to the next piece, so on and so forth. The important thing with BNCs is they're versatile. They could be made in 50 ohm or 75 ohm designs. They're a lot easier to use than threading on and off versus an N-type, and they're very difficult to break because the head has a spring finger design. There was a little bit of a limitation, though, that the frequency was only rated to 6 gigahertz. So that's when I discussed earlier how test results originally topped out at 6 gigahertz for a lot of data sheets. Since then, we now go to N connectors for a lot of our test equipment, so we can actually go much higher when we report. Impedance is stable at 50 or 75 ohm, and with a simple twist lock, it's easier to reduce any field failures because once it's positively locked into place, the connector isn't going to move or twist or go anywhere. Then came SMA connectors, the sub-miniature series. Originally designed to fit semi-rigid and some semi-flexible coax, typically at 0.141 inches and below, as frequencies were going much higher, even well beyond 18 gigahertz. The nice thing was, it was an easy product to use to replace BNC and TNC connectors because it's half of the overall diameter. A very robust design with the threading, which was very easy to twist but not over twist and lock into place. Frequencies could be rated up to 40 gigahertz. Now I'll also take that with a little bit of grain of salt, is that most typical SMAs are actually rated between 12 to 18 gigahertz. There is what's known as the K connector, which is an SMA version rated up to 40 gigahertz. An excellent low noise properties. So the big debate, BNCs versus SMAs. BNCs were stable for a lot of the handheld manufacturers since the 1960s. But when the SMA really hit the market, it was starting to become clear that BNCs had a lot of limitations, especially once you got above 4 gigahertz, because the BNCs tested SWR was 1.5 to 1, and as it got to 6 gigahertz, it went up to 2 to 1. So SMAs stayed stable at 1 to 1 throughout the entire frequency range. SMAs then became major contenders in the 1980s and 90s as the cost started to drop. Also, we had a big wireless boom. A lot of the devices were being made smaller and smaller, so the SMAs were designed to reduce the footprint. The nice thing with SMAs is that it's easier to work with very lightweight cables. The 316 that I talked to you about earlier, that's designed to go into the top of your HT, using it on other microwave discrete devices. BNCs are still out there today, as we talked about. They're used with the QRP crowd, but still have a happy life being used in HDTV applications. They're used in a lot of studios today. So let's talk about some best practices. One with your coax, look at the highest frequency you're using and the distance you're going at, not the largest, biggest coax. A lot of people take into account that losses mean everything, and that is very true and very important, but the reality is, for a 15-foot piece of coax, it's easier to use a smaller diameter of a 240 than using an RG8 size, the 400 series, or using the 600 series. Take into account that RF power equals heat. When you have SWR, that will translate into heat. As you're running a linear amplifier, that will translate into heat. If you're using a PL259 and you're not perfectly matched at 1:1, which, mind you, is extremely difficult to do in some cases, that will translate into heat as well. So give yourself some room to meet some expectations. When the coax cable is listed for a maximum power, that means in a perfect 1:1 application. But if you're using something with a PL259, my suggestion is give yourself about a quarter of the power rating as space, just in case the SWR changes. Also, with a lot of the radios using tuners, the multi-tuner devices that are out there, the ones in the radios can start at 3:1, but a lot of them go much, much higher, up to 12:1, and even a little bit higher in some of the other practical applications. So give yourself a little bit of room, because as your tuner mismatches, to find the perfect match, there's going to be some heat buildup. Sealants, tapes, coatings are always your #1 insurance for long-lasting cable. A lot of people just hook up the connector and call it done. In reality, you want to at least put some sort of sealant down there. There's a lot of hand sealants that are moldable. You just put a simple wrap on there. Coaxial, for example, is a great mastic product, but there are good ones from 3M as well. Once you tape it on there, you mold it into place, and you'll be good to go. Also, understanding your assembly tools. Assembly tools are very, very important. Getting good, high quality tools is always important, but also remember there's a couple of other things associated with that cost. How often do you use that tool? If somebody else has the tool, borrow it from them. 2, the tool is only as good as the blades that are built into it, and a lot of those blades can be very expensive to replace. Plus, a lot of those tools are only intended for about 25 to 50 strips before it starts to wear down. So always take that into consideration as well. As the tool sits there, it may rust, it may corrode, depending on how it's built out of steel or some other material. So I'm not saying don't invest in tools. What I'm saying is try to invest in quality tools, or sometimes come to people that can assemble it for you, because there is a big business that we're into. So I want to thank you for your time today. I want to thank you for spending this with me. If you have any questions, you can visit abrind.com or give us a call or reach me personally. My email is chuck@abrind.com. Thank you and be well. Bye-bye.